So now we will study a different concept in stochastic geometry, which is known as Germ-grain model. So point process, as you said, as we have seen that they model uh, the spatial distribution of points over a space, right? If you extend this concept that instead of just having points, uh, we can have random objects on the space. So how do we model the spatial distribution of random objects which are spread on a space? So germ-grain model can be used for that. There are two components here, germs and grains. So let phi denote a point process, right? So this will be made of multiple points, and these points are known as germ. Then let's have a collection of random compact sets, right? So SIs are random compact sets, and as points are ordered like x1, x2, x3, there is a ordering of the points. Similarly, there is a ordering of the random objects also. That this is the first object, second, third, and fourth. And this random or compact set can be of any shape. They can be square or a polygon, or of different spheres of different size, anything. But the distribution should be well defined. Now what we do is we take each point and we take a corresponding grain and we shift the grain to this point. Okay, so first will be shifted here, second grain will be shifted here, third grain will be shifted here, and the fourth grain will be shifted here. Okay, so xi plus si is the ith grain, the shifted grain will be known as xi plus si, which is shifted to the center xi. So union of all these shifted sets, right? If I look at all these grains, so these points are germs, and around that we have a random object which is corresponding grain. And if I look at the union of the area covered by this set, that will be given as union of all the shifted object, which are xi plus xi. This union of all these shifted sets is known as the germ-grain model. And so G will also give you, if you take the area of G, you will get the occupied area. And if you take, suppose this is a D-dimensional space, so RD minus G would give you unoccupied area. So using this, you can model the distribution of random objects in the space. You can compute various metrics such as how much area is covered, what is the probability that a particular point is covered, or what is the vacancy. A interesting point, category of germ-grain model is Boolean models. So they are also the simplest one. A Boolean model is a germ-grain model where the underlying germ PP is a Poisson point process with density lambda. Okay, so the point germ-grain model has more general. There can be any point process and any random collection of subsets. Here we have the germs are distributed as Poisson point process, and there is one more condition that SIs are independent and identically distributed. Okay, so there can be still any distribution, but it's just that all SIs are identically and independently distributed. And SIs can, if you see the corresponding one, there are XI point and corresponding complex set is SI. So SI can be seen as a mark of XI, okay, and is an independent marking because each of the marks are independently distributed. So here you can see SIs is more complicated than the natural marks we have studied in the past, that these are random variables. But here SIs are not random variable, but a random objects, right? But more or less, they can still be seen as a random quantity. And you can define them in terms of random vectors. For example, you can define rectangle in terms of a random variable. You can also, a random vector, you can also define sphere in terms of random radius. Okay, so but suppose there is a collection, the other way to look at it is also that you make a collection of sets Si. Okay, and then you just say that uh, I'll be a mark in R such that Si equal to S. Okay, so the indicator, the number of the this selection, so you make a collection of sets and then you just assign a number to each point which will denote which object in the set it corresponds to. Okay, so if I say the mark is 1, it means it's a random object associated with this S1. If it is marked as 3, it means the random object is associated with S3. So there are multiple ways you can look at this, but more or less SIs are connected with XIs and they can be seen as a mark. Okay, so what are different things we can get? So this is like the Poisson point process, and if you assign like spheres, so SIs can be like deterministic space of same radius, you will get this, or they can be of different radius and you will get different set of this at each point. Similarly, instead of sphere you can assign lines, and this will be the Boolean model you will get. So interesting point would be, given a Boolean model, what is the intersection with a set, a deterministic set? Okay, so let K be a compact set in R, and we are interested in knowing, for example, what is the intersection area or how many circles are intersecting this set K. So how do we compute this? Let us construct a new point process by retaining only the germs xi such that the corresponding grain has some intersection with k, right? So you go to each point and ask, is your grain intersecting with this set k? If they say yes, you retain that point, otherwise you remove the point. So the retaining indicator is that xi, what you want to retain based on the event that the shifted grain, right, xi plus si, the intersection with k is non-empty. Okay, so you go to each point, calculate this, and whoever gives ones, you will retain that point. Okay, and the new point process, let's denote by phi k, will be consisting of all this point, so it can be written as it is made from all xi in phi such that xi plus si intersection with k is non-empty. Okay, now you look at this in each, when you go to each point and ask this question, the location xi and the si, it is independent of other points. So the retaining event is independent across 2 points, right? For example, this one will have this own grain and this will have its own grain. This will be retained if its grain intersects with this. This will be retained if the grain intersects with this. And since both grains are independent, their intersection is also independent, and this, so the retaining is also independent. So you can think that these, it can be seen as independent thinning. You're going to each point and thinning the point, but the thinning event is independent across points. So the derived point process should also be a Poisson point process because you are doing a independent thinning of a PPP. Okay, so if the derived point process, which is made from all the points which intersect with xi, is a PPP, this means that if you ask what is, right, so that is one result. So if you want to calculate how many points, retained points are there in a set A, so that we can compute because we know that it's a Poisson random variable. And if we somehow compute the expectation of it, this, the number of points will be Poisson distributed with this mean parameter. So now we can also answer this question. So total number of points in a in the total area, right? So how many points are there such that their grains intersect with this scale? Okay. So that will be actually given by the total number of points in the derived point process. Okay, so we can say nk is the total number of points, number of grains which intersect with k is given by the total number of points in this derived point process in complete space Rd, and that will be given by summation over all xi over the indicator that the grain intersects with k. So how can I compute this? The mean measure of this, because we know that nk is a Poisson random variable, right? The number of points in any set is Poisson random variable because phi k is PPP. So nk is Poisson. We only need to know the expected value of nk to fully characterize it. To expected value of nk is given by the intensity of this derived point process over the whole space T is given by expected value of nk, which is expectation of phi krd, which is given by indicator that summing over all indicator that the grain intersects with k. Okay. Now we can apply Campbell theorem here. We can treat Si as or this complete thing as a mark of each point, and then you can say this is equal to lambda into integration of fx dx, and because f is depends on mark, so there would be expectation with respect to mark, right? So just recall the Campbell theorem of a marked Poisson one process, you will get this result. So lambda into expectation of this function dx. Now my claim is that this indicator is nothing but the indicator that x belongs to the Minkowski sum of s bar and k. Okay. So how do I show this? So here S bar denotes the mirror of the set. So if S is a set, you take each element and you reverse it. So S bar is made from all the vectors such that minus V is in this original subset S. And A Minkowski sum of B is defined as if A and B are two sets, you take each element from Y and Z and you take their summation. So Minkowski sum is made from that. So x plus s intersection k, right? X plus s intersection with k is non-empty. This means that there exists one y in s such that when you add x to it, it also belongs to k, right? So we can say there exists one y in s and one z in k such that x plus y equal to z, right? Then only there will be an intersection, right? If adding x to one element of s gives you the element of k, right? Then only there will be one intersection at least. And if there are more intersection, then there will be more pairs of y and z, right? But at least there should be one y and one z such that x plus y equal to z, right? And we can also say this in other form that x, it should be equal to minus y plus z, right? So there should be one y and one z such that x equal to minus y plus z, right? So this means that, see, if the x is such that it is it should be equal to minus y plus z, right? So this means uh, that x should be an element of the Minkowski sum of s bar and k. Right. So only then, so see, S bar Minkowski sum of k is made from all the vectors which are minus y plus z, right? So if y is in S and z is in k, S bar Minkowski sum of k is made from all such y and z such that y belongs to, S Minkowski sum k, S bar Minkowski sum of k is made from all the vectors uh, minus y plus z such that y belongs to S and z belongs to k, right? And if x is equal to one of such pair, then x should be in the Minkowski sum. Okay. If x does not belongs to this set, then there cannot be any vector y or z such that x equal to minus y plus j. Okay, so they are equivalent. So I can say that this indicator is same as saying that x belongs to S bar when calculate sum of k, right? So you just treat this as a vector k, and then if I integrate, right? So firstly I do is I take the expectation outside. So I will get lambda expectation of integration of indicator x belongs to a dx. Let's call it a. And then outside there is expectation. So lambda expectation integration of indicator x belongs to a dx. And we know that if you integrate a indicator of a set over the space, you just get the area of that set. So here I get lambda expectation of area of this set A, which is S bar Minkowski sum K. So what I get is it is equal to lambda E S bar Minkowski sum of K, its area. Okay, and we can see that this is a finite, if this is a finite value, this means total number of points in the set is finite. Okay, and so this gives you that nk is finite and is a Poisson random variable with nkrd, right? Only if the Minkowski sum is finite, and if S bar is is a compact set, is with finite moment, and K is also a compact set, then the Minkowski sum will also be a compact set. So we can use this result to compute number of grains covering origin, right? So remember, number of grains covering origin. I mean that the grain, the origin is a part of grain. So origin is inside the grain, right? This means that if I compute the intersection of origin with the grain, that intersection should not be empty, right? So we can get this expression for this by just putting k equal to 5, if k equal to 0, right? So if k is a set containing only origin, right, then if this value that x plus s intersection with k is non-empty, this means that uh, uh, right, if I put k in 0, this means x plus s intersection with origin is non-empty, right? This means the origin should be in x plus s, right? Because origin is just a single vector. So if origin is inside x plus s, only then the intersection will not be empty, otherwise intersection will be empty. So here this indicator that there is an intersection of grain with K is same as saying the origin is inside the ith grain, right? Or origin is covered by the ith grain. Okay, so if I compute N0 here, what I will get is total number of grains which cover 0. Okay, and from the previous result, we know that total number of grains which is covering origin is a Poisson random variable with mean lambda 0 RD. How do I compute this lambda 0 RD? Right, you can go the derivation, or we can use the direct result that lambda E Minkowski sum of S bar and K here is only origin. So Minkowski sum of anything with with a singleton set is just shifted, that grain shifted to the that set, and if you compute the area, that shifting does not matter. So this is just lambda E of area of S bar actually, but the S bar and S will have the same area. Uh, the inverting of the set does not affect this area, right? Or you can go it one by the basic principle. I want to compute this. This is the independent reasoning. So expectation of n is equal to expectation of this. So expectation that 0 belongs to x plus s dx, and then I take the this is same as saying that minus x belongs to x dx. Okay, now I can just substitute x to minus x, right? And this dx will become minus dx, and the integration limit will change. So eventually you get is lambda integration expectation of indicator x belongs to x dx. And this just means that it is the area of S. So this will be lambda into expectation of area of S, right? So probability that origin is not covered is given by the probability that nk equal to 0. Nk is a Poisson random variable with this mean. So probability that nk is 0 is given by exponential minus lambda es. Okay, right? So probability that a random variable, which is Poisson random variable, is 0 is given by e to power minus mean of the random variable. Mean is this. So probability that is not covered is will be given by this, and probability that is covered will be given by 1 minus this. So what are the examples of Poisson, this Boolean model? One is we can use, or examples or application actually, we can use Boolean model to model blockage processes, right? So you can, blockages means, if you look at a cellular network, each link can be blocked by some building or some object, right? So this is a user, this is B1, B2, B3, B4, these are all base stations. And these green ones are buildings, which can be in shape of rectangles, or L shape, or half arc shape. And if this building falls in any of the link, then that link will be blocked. Okay, so like this, there is no building in between, so this link is line of sight. But this link, there are two buildings, so this is blocked. Okay, and sometimes the total number of objects also falling on the link will tell the severity of the blockages. So we can mod, this is like random objects spread over the space. So we can use Boolean model to model them. We can treat centers as Poisson point process, and then links. So these blockages are then its orientation, and then length or the size can be randomly distributed. Okay, so we can take circles, squares, random objects to take the blockage shapes. A very simple way would be to actually use lines to model these blockages, right? So lines are simplification, but they can very well approximate the blockages by looking, you can treat them as the projection of the building over the perpendicular of the line, right? So eventually you are going to cut the building. So if I have the projection, if I model them correctly, you can get some simplified but yet very good blockage models from that. So we can treat centers as PPP, the line centers, and each blockage is modeled as line, and the length of the line and the orientation of the line can be random, right? So if we take random length, so distribution is given by FLDL. We can take, for example, L as a uniform random variable with 0 to some maximum length of blockages. Similarly, random orientation theta, which can have some distribution, and we can also take like uniformly distributed theta between 0 to 2 pi. So let us understand what is Minkowski sum. As we said, Minkowski sum is defined as if A and B are two sets, the Minkowski sum of A and B is defined as you take each vector in A and each vector in B and you add them, and if you take the subset of all such additions, you get the Minkowski sum. So suppose there is a line, so this is set A and this is set B. What is the Minkowski sum of this? So what you do is you take each vector from this and add this vector. So if you add, take this and add this vector, the point corresponding to this, you get this line shifted here. Okay, then you take again each point of this and add the next point, which is here, you get this point shifted here. Okay, similarly, as you take all the points here, you get this set shifted here, 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 here. And if I take all these points, what you get is a this structure, that this is shifted with the centers at each point of this. So eventually I get a parallelogram. Okay, so the Minkowski sum of two lines will be a parallelogram. The other examples you can also see, suppose I take Q1 and Q2 and I have computed the Minkowski sum of this. You take each rectangle and shift to each point of the vector, right? So basically what you have to do is you have to take each point here and shift it to each point there and basically add it, and then you take the union of that. So this you can also do by taking the complete rectangle and shift its center to each point of Q2, right? Or you take Q2 and shift its center to each point of Q1, right? Regardless of what you do, if you take Q1 and you shift it to each point of Q2, what you get is when you put Q1 here, you get Q1 here. If you get put Q1 here on the extreme side, you get Q1 like this, right? So basically what you get is a bigger rectangle with the length equal to the this plus this, and this would be this plus this. Okay. So it is like you take this object, put it center, and you keep the center inside of Q2, and you keep on shifting Q1 or different values, right? You just don't let the center go outside Q2, right? And then you get the complete set. Sorry, not the center. You take this point, the lower point, and you keep on shifting it. I don't let this point go outside. Similarly, if you take P and Q and you again do this thing, you get this structure. Similarly, if you take a circle and the rectangle, if you keep on putting circles, all these points, you get this structure. Okay, so you just work out these different examples and see how you can get Minkowski sum. So we have seen that Boolean models can be used to model a blockage process. For simplicity, let us consider linear blockages. So there is a user at the origin, and then there are different base stations, B1, B2, B3. And then these blockages are modeled as a Boolean model. So their centers are located as a Poisson-point process with density mu. And then each blockage is a line. Its length is L, which is again a random variable with some distribution. And its orientation theta is also a random variables with some distribution. So in this case, we would be interested in knowing that if I take any link of length R, what will be the probability that the link will be blocked or unblocked? So a link would be blocked if any of the blockage falls on that link. So we have to compute the probability that none of the blockage falls in this particular link, then this link will be non-blocked. Okay, so given the distribution of these blockages, what is the probability that no blockage intersect this line? Right, that is the probability we are interested in. So we have already shown that we have computed the probability that the blockages intersects with set K. Okay, so here the set K is this line. So we have to compute the probability that these blockages intersects with none of the blockages intersects with this line. And we know that it's a Poisson, the number of intersections falling on number of blockages falling on this set is Poisson random variable. So if I compute the mean number of links falling on this link, then from that I can compute the probability that none of the blockages fall on this link. So how do I compute the mean number of links falling on this? For that, I have to compute the expected value of as a mirror set into Minkowski sum of K. Okay, so here the grain S is basically a line. So it will be given by each point of this line will be given by L cos theta comma L sin theta, where L is between L by 2. Okay, so if a grain has length L and angle theta, then this line would be given by all values of x comma y, such that x is L cos theta, y is L sin theta, where L can be anything between minus L by 2 to plus L by 2. This L is the length, this one, and theta is the orientation. And these are all random variables with some distribution. Pu, that the probability that a link or length R is non-blocked. Okay, let us take the link as parallel to x-axis, right? So If the orientations are not uniform, as the angle is not uniform, then you can see that the orientation of the link also affects the line of sight non-sight probability. For let us assume here that the blockages are uniform, you have uniform orientation, right? It means the link can be, the theta is a uniform random variable between 0 to 2 pi. So first we'll compute number of blockages intersecting the link. And link is given by r comma 0, where r is less than or equal to r. So the link length is capital R. And so the link line, the line segment denoting the link will be represented by all x comma y such that x is less than or equal to r and y is 0. Okay, so number of blockages is a random variable with mean mu into expected value of s bar in Minkowski sum of k. Okay, so what is the Minkowski sum of a line and a set k? Right, the line is the length. This is set k. Okay, r of length r, and this is your s. Right, if you take s bar, you will get a mirror image of that. And if I compute the Minkowski sum of these two, what I get is a parallelogram. Okay, and the parallelogram will have length r and other length l, and the angle between them will be theta. Okay, you can also prove this using this definition of s and k. The Minkowski sum will be denoted by all possible unions of these two vectors. So basically, you will get all vectors such that r plus r cos theta and l sin theta, where this r is less than or equal to capital R, and this l is less than or equal to l by 2 mod of this, which is the parallelogram. Okay, here I have not particularly kept attention on S bar and S, right? Because if the angle orientation is uniform, you can either take S or S bar, you will get similar results. You will get the same result. So S bar and Minkowski sum of K will be given by the area of this will be given by the area of this parallelogram, which is L R sin theta. Okay, so the expected value of this will be expected value of this. Since L and theta is assumed to be independent, this will give you expected value of L into R into expected value of theta. Sorry, expected value of sin theta. There's a typo here. Expected value of mod sin theta. So because of that, what we solve it, EL will be L and E theta will be 2 by pi. So if I so this will be the mean. So probability that k is 0 is given by e to power minus this mean. So probability that the link is non-blocked, right, which is equal to probability that k is 0 is equal to exponential minus mu into L 2 by pi into R. So from this, we can compute the non-blockage probability, and also you can compute the blockage probability. So this is a result that if I assume linear blockages, any link and as in the linear blockages such that the angles are uniform, the orientation of the blockages are uniform, then the probability that a link of length L R will be not blocked with this probability. There's another way to also prove this result, where you can first take a subset of blockages with length L and orientation theta, and then you can say the event that the link ched is non-blocked by any blockages in this particular set is equivalent to the event that center of all blockages lie outside this parallelogram P. Okay, so you can look at this figure and know that if the center does not fall inside this parallelogram, then this blockage will not intersect with the link. Okay, you can try different positions, and then you can verify this, that if the center falls outside this parallelogram, then the blockage will not intersect this link. So the probability that this link will not be blocked is same as probability that none of the center falls inside this parallelogram. And if the centers are PPP, so the probability that none of them fall inside a set is given by the void probability of that set, which is equal to exponential minus mu into size of A, which is area of A. So area of A will be given by LR sine theta. So the probability that none of the blockages fall inside this is given by e to power minus mu LR sine theta. Okay. And here mu is the density of these particular blockages, right? So again, these blockages have a particular length L and orientation theta, and they are the thinned version of the complete blockage process. Because in blockage process, you have all kind of L and theta. So I am basically only considering the blockages which has this particular L and theta. Okay. So, or in particular, you can say if it's a continuous case, then you will take all blockages with length falling in dl and angle falling in d theta. So the probability that the density of these blockages will be given by density of the original blockage process into the retaining probability. Retaining probability would be given by the probability that you have a length L and theta, orientation theta. You multiply by mu, you will get the density of these particular blockages. Okay, so if I put the value of mu dash there, what I get is exponential minus mu f1 dl f t theta lr sine theta. Now the link is not blocked by any of the blockages. It means you have to consider all these subsets of blockages, and then the link should not be blocked by any of them, right? And because they are independent, right, thinning, we have proven this result that if you thin a point process and get two different point processes, both will be Poisson and both will be independent of each other. So the total probability the link will be not blocked is given by product over all these probabilities of individual blockage of length L and theta. Okay, and if you put that and you give an argument, you will get arrive at the same result. Similarly, I can extend this analysis to rectangular blockages. Instead of lines, I can take other objects also. Let us say what will happen when I take rectangular blockages. In that case, the Minkowski sum of blockage and set K will be given by this particular shape, which is PVUTSQV. And the area of this will be given by parallelogram plus these two triangles. Okay. And from that, you can compute expected value. And so the probability of line of sight will be given by exponential minus beta r minus p, where beta is given by this. Here you can see both parameters, expected value of length and expected value of width is given, is dependent on both of them. And similarly, this p is given by the mu into EL into V, which is area. Okay, so this is is a dependence on kind of perimeter, and this is area. So both factors here play a role. Similarly, you can also compute the probability that two links are blocked together. Okay, so suppose I have this link R1 and R2, and I want to compute that both links are either blocked or unblocked. You can see there is a correlation. Normally in analysis, many times we take this independent, right? The links are independently blocked or not. But in reality, there can be some blockages between the two links also. Okay, so how do I compute this joint blockage probability? For simplicity, let us take two base stations located at R1 and R2 distance and angle phi. Assume one base station is at x-axis, right? So you have this B1 and B2. Now, by the same argument, you can prove that both links will be unblocked if none of the blockage centers fall in this union of parallelograms. Okay. Again, you can also prove this by using the Minkowski sum argument. So here we are interested in non-blocking of this link, right? These two links. So if I consider the set, my set K would be the union of these two lines. And number of blockages falling on these two Number of grains falling on this link, this union of link set K will be given as the Minkowski sum of this set K and the blockage. Okay, so this will give you the union of two parallelograms. Okay, the area of the parallelograms you can compute is given by this particular form, and then you have to compute the expected value. Okay, and then from expected value you can compute the blockage probability, which will be given by this. Another example where we can use Boolean model, which is so the example we are going to cover is the coverage area of a base station's network. So let phi denote the base station process, and so phi is set of xi's with density lambda. Now each point xi, let us define the grain of this point as the SNR coverage, right, area. So which is defined as set of consisting of all location y such that SNR at a receiver at that location will be more than tau. Okay, so you go to each point and you define the grain of this as a set of all locations where the SNR from this point is more than tau. Okay. So suppose there is no fading, then the SNR, so if there is a point xi, the base station at xi, the SNR at y is given by transmit power into the distance between xi and y to power minus alpha divided by noise power. And this is more than tau if this value is more than tau, which gives that xi minus y should be less than p by n tau into 1 upon alpha. Okay, so all the locations where the distance from xi is less than this value, their SNR will be more than tau. Okay, so if xi is fixed and this is expression y, you can see that this is nothing but an expression of a circle. This will denote a ball around xi with radius this, right? All y falling in that ball will have SNR more than tau, right? So grain is nothing but a circular region around xi with this radius. Okay, so grain of point xi is a ball centered at xi with this radius. And the expected value of SI is given as area of this ball, which is in 2 dimension, it is pi r square, which is pi into p upon nt to the power 2 by alpha. Okay, so probability that a point origin is not covered, right, it is given by the probability e to power minus lambda into area of the grain, expected area of the grain, right? So probability that a location or the origin is covered, in other words, is intersected by a grain, is equal to 1 minus exponential minus lambda pi p by nt 2 by alpha. So similarly, this will give you, so this will give you the probability that a point is covered. Now, if you include fading, then the SNR at y there would be one extra variable hi. Probably the event that this is more than tau would be given that if this value complete receive power is more than tau, right? And this gives xi minus y should be less than hip and tau upon 1 upon alpha. So this is now a random grain where there is a fading also. So hi will depend on what is the size of this. So Si is a ball located at xi with this radius. So expected value of area of Si would be given by pi r square. R is this, and then there's expectation. Only hi is a random variable, so you get pi p upon n tau to power 2 by alpha e expectation of h to power 2 by alpha. Okay, so from this you can compute the probability that the point is covered or not, by any grain or not. Okay, so this kind of gives you that if there is a base station process in the area and you just want to know that over all space, how many points are covered. I mean, what is the fraction of points which fall in the SNR of some base station, right? And this can help you decide the density, right? You want that as more many points, at least, like for example, you want 99% of the point to be covered. So you can compute that in case of Poisson deployment, what is the density I should keep, right? Such that uh, all the 99% of the area is covered by at least one base station. Okay, another way to compute ESI is you can also compute by taking the expected value of uh, indicator of y comma si dy, right? And this will give you, if I put the expectation inside, this will give me probability y is element of si. So if I take y element of si dy and I integrate it, then also I can get ESI. Okay, and probability that y belongs to si is given. So here it is, this is different than this part. Here we are compute that y should be a part of any grain, right? Here we are interested in probability that y is a part of the ith grain. Okay, if I can compute that and I integrate that, from that I can also get the expected value of si. Okay, so what is the probability that y belongs to si? This means the SNR at y from the ith grain is more than tau, and this means the SNR is given by HR into power into xi minus y to power minus alpha divided by noise is more than tau, right? Probability of that is you can write this in terms of HI is more than tau into noise divided by transmit power and xi minus y to power minus alpha. So probability that HI is, this is a deterministic value. Probability that HI is more than some theta is exponential minus theta if HI is a exponential random variable, right? If you consider Rayleigh fading, then you can get this result. So I get E expectation exponential minus tau n upon px minus y alpha. And if I integrate this over the space y, I should get the expected value of Si. Okay, so for d dimension 2, I can use polar coordinates to get this expression. So dy become 2 pi y dy, and then you have this. And then you can substitute t equal to tau and p pi alpha, and then when you substitute, you get this expression, and you get this particular expression, right? This is only for exponential random variable, right? So this method works if you have Rayleigh fading, but for other fading variable, this expression may get very complicated, right? But in any case, whatever the case is, here would have a expectation of h to pi alpha, and depending on the different fading variables, to get different values. Let's move to SIR coverage area, right? So these grains can be anything. In the previous example, I have taken grain as the SNR coverage of each point, right? Which are independent across points, right? Now, if I take SIR, then for each point xi that define the grain of this point is defined as SIR at receiver at point is more than tau. So this is given as p xi minus y to power minus alpha divided by interference, and I want this to be more than tau, right? So we use the method we used in the previous slide, that expected value of area of SI is given by if I integrate probability that a point belongs to SI over the space. Now a point belongs to SI means the SIR at the receiver located at distance y from transmitter at xi is more than tau. Okay, and that we can compute. We have already computed in the past, right? So remember, if in the ad hoc case, if I take a point y and this transmitter is located at r distance, and then there are Poisson interferes, then the probability that the SIR from this transmitter is more than tau is given by exponential minus lambda pi tau 2 by alpha into C, which is path loss gain, into r to power alpha. Okay, here I have taken alpha equal to 2, but it can be any alpha. So get this expression for pathless alpha, and then you can, the remaining would be to compute the expected value of SI. So you integrate this to compute expected value of SI, and from that you can basically compute probability that none the point is so, okay, so that will give you, yeah, but then you cannot compute what is the probability that a point is covered SIR, because this model is not a Boolean model, right? Why? Because in Boolean model, we assume that all the grains are independent. Here, the grains are not independent because uh, because of the interference, right? So we know that if two links are close by, the interference is large. So if one grain has a smaller SIR coverage, the other grain nearby will also have a small SIR coverage. So because of that, these grains are not independent. So this is not a Boolean model, right? So you can no longer say that the intersection with any set K is a Poisson random variable, and because of that, you cannot compute the probability that the point is covered in the same way we compute for the SNR coverage.